This is Linear Algebra Section 1.1 video, Systems of Linear Equations. A linear equation in the variables x1 through xn is an equation that can be written in the form a1x1 plus a2x2 plus on up to a sub n x sub n equals b, where b and the coefficients a1, a2 through an are real numbers or complex numbers, and n can be any positive integer. Some examples of linear equations: 3x1 minus 5x2 plus 7 equals x1. So x1 is repeated, but this is still a linear equation. Also, x3 equals 5 times square root of 3 minus x2 plus 2/3 x4. So the coefficients can have radicals or fractions, but the variables, the fraction can't happen to the variable itself. It can happen to the coefficient but not to the variable. If it does, then it's nonlinear. So here's an example: 3x1 minus 5x2 equals x1 times x2. So the fact that we're multiplying our variables here means it's nonlinear. And then x3 equals 3 square root of x1 minus 5. Because the variable is under the square root symbol, then this makes this a nonlinear equation. A system of linear equations, or a linear system, is a collection of one or more linear equations involving the same set of variables, x1 through xn. And then a solution of the system is a list of numbers, s1 through sn, that makes each equation in the system a true statement when we substitute those values for the variables respectively. So here's an example of two equations and two variables. We have two equations being graphed. x1 minus 2x2 equals negative 1, and then negative x1 plus 3x2 equals 3. So the first equation is our red line and the second equation is our blue line here. When we graph two lines, the solution is the point of intersection. So in this case there is one solution, and it is the point 3,2. That's the intersection point. There could be other possibilities. Two other possibilities are when we have parallel lines, and here's an example of two equations. x1 minus 2x2 equals negative 1. Negative x1 plus 2x2 equals 3. So there is no point of intersection, so there is no solution. So anytime we have a graph with parallel lines, there is no solution. And in our next system, we're going to graph the two lines. x1 minus 2x2 equals negative 1, and negative x1 plus 2x2 equals 1. And we see that when we graph them, that our second equation ends up lying right on top of the first, because you'll notice that the second equation is simply the first equation multiplied by negative 1. And when this happens, when the two lines are the same line, then the system has infinitely many solutions. So we have a basic fact. A system of equations will have either exactly one solution, infinitely many solutions, or no solution. And we say that the system, if it has one solution or infinitely many, we say the system is consistent. And if there is no solution, then we say that the system is inconsistent. Now suppose we have three equations and three variables. Each equation will then determine a plane in space. Two variables, we have a line, and three variables gives us a plane. the three planes can intersect in one point, and then it's consistent, in a line or a plane, and then it's still consistent, or in no points, and then it's inconsistent. Some terminology. The solution set of a linear system is the set of all possible solutions of the system. Two linear systems with the same solution set are said to be equivalent systems. A strategy for solving: we replace one system with an equivalent system that's easier to solve. So in this example, we have x1 minus 2x2 equals negative 1, and negative x1 plus 3x2 equals 3. Notice that this is the first set of equations that we looked at when we were looking at graphs. Normally, we would begin by trying to eliminate x1 from the second equation. When you do that, we'll rewrite the first equation just as it is. And then when we do our elimination, we'll just need to add these two together. Notice that our x1's go away, or you get 0. You'll get 1x2, or x2 equals 2. So we'll replace our second equation with this. So now I have x2 equals 2. And now I want to eliminate x2 from the first set of equations. So what I'm going to do is I'm going to multiply here by 2, and then I'm going to add it to the next equation. So when I multiply through by 2, I'll end up with 2x2 equals 4. And then we have our first equation still. And we will add those two together. So we'll end up with x1, and x2 is eliminated, equals 3. So then we replace our first equation with that. So we end up with now x1 equals 3, and x2 equals 2. So our solution is the 0.32, just as it was in our graph. The essential information of a linear system can be recorded compactly in a rectangular array called a matrix. For example, the first system gives rise to the following two matrices. First, we can look at just the coefficient matrix, where we'll simply list the coefficients of x1 and x2 in both equations. Or we could use what we call the augmented matrix. And in this case, we'll list the coefficients and also what the equation was equal to. We can use the augmented matrix to solve the system. So we'll use that matrix and we'll solve it just like we did in the previous example. We're going to multiply the first equation by 1 so we don't change it, and add it to the second equation. So the first one doesn't change at all. But when I add these two together, so I'll just do this addition over here, I get 0, 1, and 2. And what I'm going to do is I'm going to replace this second row by my new numbers. So I have 0, 1, 2. And now I'm going to do the same thing. I want to eliminate my x2, or this negative 2. So I'm going to multiply by 2 here and add it to this row. So what I then end up with is I have 1, negative 2, negative 1, and I've multiplied this one by 2, so I'll get 0, 2, 4, and I want to add those together. So I get 1, 0, 3. What I'm going to do is I'm going to use this, and I'm going to replace the first row with this now. So my new matrix is 1, 0, 3, and 0, 1, 2. So notice that I have my solutions in my last column. So I still have the solution 3, 2. because this translates to the equations x1 equals 3 and x2 equals 2. There are 3 elementary row operations that we can use in simplifying a matrix. The first one is replacement, where we add one row to a multiple of another row. The second is interchange, where we simply interchange 2 rows, just changing the order in which we wrote the equations. The third is scaling. Multiply all entries in a row by a non-zero constant. We say that 2 matrices are row equivalent if there is a sequence of elementary row operations that transforms one matrix into the other. One fact about this row equivalence: if the augmented matrices of 2 linear systems are row equivalent, then the 2 systems have the same solution set. So let's look at this example. We want to look at this system, an augmented matrix, and we want to find the solution. So we want to solve the system. Our first step is we want to eliminate x1 from the third equation. So what we're going to do is we're going to multiply our first equation by 4 and add it to the next equation. So I'll do that up here. If I multiply the first one by 4, I'll get 4x1 minus 8x2 plus 4x3 equals 0, and then my third equation was negative 4x1 plus 5x2 plus 9x3 equals negative 9. And when I add those together, x1 cancels and we have negative 3x2 plus 13x3 equals negative 9. And you'll notice then that this became my new third equation in my system. I want to do the same thing with my matrix. I want to multiply the first row by 4 and add it to the last row. So we'll see what happens. We'll end up, the first row multiplied by 4 is 4, negative 8, 4, 0. And then my third row is negative 4, 5, 9, negative 9, and I want to add those two together. So when I do that, I get 0, negative 3, 13, and negative 9. And that replaces the third row of my matrix. Notice though that the first row is still what it was originally. We don't multiply it by 4 and change those numbers. We just did that in order to change row 3. My next step is to change x2 so that it has a coefficient of 1. So I can multiply this row, the second equation, by 1/2. And when I do that, I will end up with x2 minus 4x3 equals 4 for the second equation. And we do the same thing with the matrix. And now I want to get rid of or eliminate x2 from the third equation. So I need to multiply the second equation by 3 and add it to the third equation. And I will do the same thing with my matrix. This will give rise to this new set of equations, and our matrix is said to be in triangular form. And notice that we have ones on our diagonal, but we have a lower triangle of zeros here. So we can tell that we're in triangular form. Now to finish solving, what we're going to do, notice that we started with our first variable in our first column, and we got a 1 and then zeros underneath, and then we moved over to get a 1 where x2 was and a 0 underneath, and then we have a 1 here, which is what we needed. Now we want to get zeros above that last 1. So I want to change negative 4 to 0, and I want to change 1 to 0. So I multiply here x3 by 4 and add it to the second equation. And I will also multiply it by a negative 1 and add it to the first equation. and it'll give me the following system of equations. And notice that it eliminated the x3 variable from the first and second equations. We do the same thing in our matrix and we accomplish the same thing. We get zeros above our 1 here. The next step, we want to eliminate x2 from the first equation using our second equation. So I will multiply x2 by 2 and add it to the first equation. And when I do that, we've solved the system. We have x1 equals 29, x2 equals 16, and x3 equals 3. When I do the same thing with my matrix, notice the form. We end up with 1s on the diagonal, zeros everywhere else, and my answers as the last column. So the solution is 29, 16, and 3. And in the book they substitute those into the original system. So you're welcome to do that. Substitute that into the original set of equations and see if you get the correct answers. Now I would like you to solve this system on your own. We'll talk about the answer in class. Given a system of equations, there are two fundamental questions. Is the system consistent? That is, does a solution exist at all? And if a solution exists, is it the only one? So what we mean then, is the solution unique? So let's look at an example. Is this system consistent? This is the same system as in example 1, and we row reduced it to the triangular form. This is before we finished solving. This was about midway through our work. At this stage, we can see that a solution exists and that it's unique, that it's the only solution. So we ended up here seeing that x3 was equal to 3, and we could back substitute and find x2 and find x1 and see that we get one value for each variable. So we have a solution and it's the only solution, so it's unique. Now we want to look at example 4. Is this system consistent? So we have our augmented matrix that we want to reduce and get into triangular form. To do that, we'll use row operations on the augmented matrix. The first step, we want a 1 in the very first spot. So we'll interchange rows 1 and 2. And we produce this matrix. Now we want zeros underneath the 1s. So the first spot underneath is already a 0. So now I need to change this 5 to a 0. So I will multiply the first row by -5 and add it to the third row. And we get this matrix. My next step normally would be to change this 3 to a 1. But since we're just trying to get it into triangular form where we have zeros below, and we're not trying to solve, we don't necessarily need to worry about getting 1s on the diagonal. So I'll simply multiply by -1 and add it to the third row. That will give me a 0 underneath. And if we rewrite this in our equation form, we see that our last row gives us the equation 0 equals -3. This is never true. It's a contradiction. 0 cannot be equal to -3. When something like that happens, we say the system is not consistent. Here's an example that I want you to work on. I want you to determine, using row operations on the augmented matrix, I want you to tell if this system is consistent or not. And we will go over it in class. Example 6. For what values of h will the following system be consistent? We're going to rewrite this in our augmented matrix, and I have 3, -9, 4, then -2, 6, and h. and I want to get it in triangular form. So the first thing I'm going to do is try to get a 1 in my first spot. So I'm going to multiply through by 1/3. And when I do, I end up with 1, -3, 4/3, and my second equation is the same. Next we want to get a 0 underneath the 1, so I'll multiply this equation by 2 and add it to my last equation. So I end up with 1, -3, 4/3, and let's do the work for it. When I multiply by 2, I get 2, -6, 8/3, and I want to add that to -2, 6, and h. So when I add that together, I have 0, 0, and then h plus 8/3, or 8/3 plus h. So I'll replace my second row with that. 0, 0, h plus 8/3. So now I want to determine if it's consistent or not. If I convert it back, this means that I have x1 minus 3x2 equals 4/3, and then I have 0 equals h plus 8/3. So this equation, it tells me that it's consistent only when this equation is true. So we need to solve for h to find what value of h will make that equation true. So to do that, I'll rewrite my equation, and to solve I subtract 8/3 from both sides, and I end up with h equals -8/3. So that means that this equation or system is consistent only when h equals -8/3.